last day of notes plus clarification. Okay, so we talked about how for every standard deviation we move in x, the predicted y will move our standard deviation in the y direction. Okay, and this is a picture where it's been standardized, and this is where we left off. So far we've been working with standardized values, so this would be the equation of the line of best fit. Basically it's y hat equals mx plus b, where b equals 0, or we could be more AP stats with that and say that it's y hat equals b sub naught plus b1x, where b sub naught equals 0. Okay, so that's just rewriting it, y equals mx plus b. And again, we've standardized it. We've taken the z-score for every data point, so it's actually, right here would have been x bar, y bar, and then you've got a line going through it. And what this is a derivation to show how we get our different values when we have you plug stuff in. So you could take the formula for z-scores and put the z-score for y and the z-score for x into the formula. And then right here, this is the point slope formula. Remember, y minus y1 equals m times x minus x1. And since we know that the only point that it has to go through, the line of best fit has to go through, is x bar, y bar, that's right there. And we've also learned that the slope of the line of best fit is r times the standard deviation of y over the standard deviation of x. This last little bit is just showing you how you could solve for it. So they go ahead and they distribute the slope and get down here, and you know what, I really just don't think the rest of that derivation is that necessary. Although what it is showing you is that, again, your slope is this. Okay, the whole point of this is to solve problems like in your homework on page 198, number 46. So I'm going to do one for you here, and then you should be able to do the homework. And what we're going to do is we're going to use the formula, and then what they can do is they can give us the x bar, the y bar, the s of y, and the r, and the s of x, sorry, all of the pieces to fill into the formula and find the best line of best fit. So what we have is y hat minus y bar minus y bar equals the slope, which is r times s of x, s of y over s of x times x minus x bar. So this is actually just a plug and chug activity. This was a kind of scary looking derivation, but we're using it just to plug and chug. So then it's saying, okay, let's plug in our x bar right here, our y bar right here. We can plug in our r for s of y and our s of x and solve for the least squared regression line. So I'm going to do that. I've got our y bar minus 150 equals our r of 0.62 times s of y, which is 30, over s of x, which is 4, times x minus x bar of 65. Okay, simplifying that, I get y bar minus 150. Multiply this stuff to get together, and I get 4.65x minus 302.25. And what I did there is the 4.65 is all of this, and the 302.25 is 4.65 multiplied onto that, 65. So I just distributed. Lastly, we can add 150 to both sides, and I get a y bar equation, or a y hat equation, least square regression line of 4.65x minus 152.25. So this is exactly how you would do problem 46 if you haven't been able to do it. Just a couple notes. Note, unlike the correlation coefficient, x and y are not interchangeable. This is some last information unrelated to what we just did when calculating the least square regression line. Therefore, we should never use a y value to try to predict an x value. You might actually get the same linear regression line, but the r's will not be the same. Note, if r equals 0, and the slope equals 0, and the least square regression line is horizontal, so there's absolutely no linear association. Knowing x won't help us predict y.